Hey everybody, welcome back. In this video, we're going to take a look at capacitor circuits with direct current. We're going to look at configurations of both series and parallel capacitors. And we're going to do examples of both parallel and series capacitors. And finally, we're going to end with a summary table of all the rules for analyzing capacitors in both parallel and series. Now you might ask yourself, why is it that we're starting with parallel first, whereas with resistors, we started with series first? Well, it's because the pattern for equivalent capacitance in parallel is the easier pattern. And I like to start with the easier pattern first. And you might notice that this looks a lot like the pattern that we had for resistors in series, whereas capacitors in series follow the pattern that we saw for resistors in parallel. So we do see here a flip-flopping of the structure of the equation for equivalent capacitance compared to equivalent resistance in series and parallel. All right, let's get into some introductory concepts involving some old equations that we want to bring back. So in our previous chapter, we looked at electric potential, and we defined capacitance as the amount of charge that could be stored per unit voltage. And if you rearrange that equation, we can get the amount of charge is the product of the capacitance and the voltage. Now, this rule we're going to learn can be applied to both individual capacitors and entire capacitor circuits. Likewise, this equation that we saw for the amount of potential energy that can be stored in a single capacitor, that also can be applied to entire capacitor circuits as well. So we're going to bring back these equations and use them for analyzing capacitor circuits. When we look at capacitors in parallel, we want to start out with a basic diagram. So our diagram will start with a voltage source. So here is our voltage source. Here's our positive terminal and our negative terminal, of course. We're going to call this our EMF. Now, what I've drawn there is an uppercase Greek epsilon, and that stands for EMF. EMF, of course, stands for electromotive force. And we're going to hook up this battery or voltage source, whatever it happens to be. We're going to hook it up to a single capacitor. We're going to call this capacitor C1, followed by another capacitor, which we're going to call C2. Now notice we've arranged these capacitors in parallel, which means that we're allowing multiple paths for the current to flow. So what we see here is that in parallel, each capacitor receives the same voltage provided by the EMF or provided by the battery. Now, this is the same pattern that we saw for resistors in parallel, where we also saw the same voltage was provided to each resistor. So the same pattern we're seeing here, that in parallel, each capacitor gets the same voltage. And the equation, as we saw earlier for the equivalent capacitance in parallel, is C equivalent is equal to the sum of all capacitors, or C1 plus C2 plus ... And as a result, because adding a new capacitor will just add on an extra term, adding a capacitor in parallel will therefore increase the overall capacitance of a circuit. Now, we might ask ourselves, why is it? Why is it that adding a capacitor in parallel will, as we said, increase overall capacitance of the circuit? I'd like to provide you with a bit of an explanation. So once again, let's draw the battery or the voltage source. And let's draw, in this case, let's draw 3 capacitors in parallel. Now notice I've drawn these almost end to end. And I've done that to highlight an idea. So let's say that each of these capacitors has the same distance d across the plates of the capacitor. And let's say that each of these has a certain area. So let's call this area A1, call this one A2, call this one A3, whatever they happen to be. Is it fair to say that because capacitance for a parallel plate capacitor is kappa times epsilon naught times the area of the capacitors divided by the distance, is it fair to say that by arranging all of these in parallel, keeping this distance the same or constant, is it fair to say that by adding essentially more area for the charge to build up on, when that area gets bigger and everything else stays the same, that capacitance is also going to increase because we're able to store more charge in the circuit than we were able to previously. And because the charge is equal to CV, if that voltage source, if that EMF remains the same, then an increased capacitance means that we can store more charge. All right, so this is just a nice visual way of imagining how adding more capacitors in parallel really is just beefing up the area over which we can store charge for a given voltage. Okay, let's take a look at our first example. In this example, we're going to calculate the total capacitance of an entire circuit, the total charge stored on that circuit, the energy stored in that circuit, and then we're going to look at an individual capacitor in the circuit to find both its charge and its energy. So let's start with the total capacitance of the entire circuit. So that's part A here. So in this case, we're going to say C equivalent is simply C1 plus C2, or we've got 3 microfarads plus 1 microfarad. And you might be asking yourself, why are we dealing with such small amounts of capacitance, microfarads? Well, it turns out that 1 farad is actually an enormous amount of capacitance. And most circuit boards have capacitances on the order of micro or even nanofarads. So that's why we deal with such small amounts of capacitance. So 3 plus 1 would yield 4 microfarads of capacitance. Easy enough. All right, the next one is to find the total charge stored. Now, you might recall from our last chapter on electric potential that the charge stored on a capacitor is equal to CV, right? Well, if we want the total charge on the whole circuit, that'll just be the total capacitance times the total voltage, which is just the voltage. So we'll just call that V total if we want. And so the total capacitance that we just found was 4 microfarads, right? So this is 4 microfarads times the voltage, which was 12 volts. If you go back to the diagram, it was 12 volts there. So the product of 4 and 12 is 48. We're all in SI units here. Farads and volts are both SI units. And the product of a farad and a volt is going to be a coulomb. So this is going to be 48 microcoulombs of charge. And there we go. We found the total charge stored on the circuit. All right, let's take a look at part C now. So part C says, find the total energy stored. And this is where we're going to bring in the equation for potential energy. U equals 1/2 CV squared. And this is going to be 1/2 the capacitance of the circuit, as we said before, was 4 microfarads. The voltage is 12 volts. This is all in SI units. So 1/2 of 4 is 2. 12 squared is 144. 2 times 144 is 288. We do have a micro in there, and the unit of energy is going to be joules. So we have 288 microjoules of total energy stored in this capacitor circuit. All right, let's take a look now at part D. So part D asks us to find the charge stored on capacitor 1. I'm going to call that Q1. And Q1 is going to be C1 times V1. So if we go back and look at our diagram, if this is capacitor C1 and this is capacitor C2 over here, the capacitance of the 3 microfarad capacitor is 3 microfarads. So that's our capacitance. So 3 microfarads times the voltage. Now, like we said, in parallel, every capacitor gets the same voltage, right? We said that right here. In parallel, each capacitor receives the same voltage. So going back to our calculation, the voltage across the first capacitor will just be 12 volts. So 3 times 12 is going to be 36 microjoules. joule, or rather microcoulombs of charge. And we ask ourselves, is it plausible that that capacitor could have 36 microcoulombs of charge? Well, the total charge we found was 48 microcoulombs. And 36 microcoulombs is certainly less than 48. So it's plausible that that is the amount of charge on that capacitor. And as we can see, the amount of charge that we find is actually proportional to the amount of capacitance in a parallel circuit with capacitors. So more capacitance means we can store more charge. So whereas capacitor C1 gets 36 microcoulombs of charge, we would find, obviously, that charge Q2, or the charge stored on the second capacitor, would be the difference between 48 and 36, which is 12 microcoulombs. But anyway, let's take a look at part E here. So part E says find the energy stored on the 3 microfarad capacitor. Well, we're going to call this energy 1, or potential energy 1, is equal to 1/2 C1 V1 squared. So this is 1/2 times the 3 microfarad capacitor times the voltage. Again, everybody gets the same voltage in parallel. So that's 12 volts squared. And if we take 1/2 of 3 is 1.5 times 144, it's going to give us 216 microjoules of energy. Is it plausible that that capacitor would store 216 microjoules of energy? Well, the total energy was 288. So yes, it is plausible that that capacitor would provide 216 of the 288 microjoules of energy. All right, very good. And that completes our example on capacitors in parallel. Let's take a look now at capacitors in series. So our diagram will look a little bit different this time. So let's start with our EMF, our voltage source here. And then, oops, drew that backwards. And then let's draw our first capacitor, C1, followed by a second capacitor, C2, in series. All right. In series, each capacitor is going to receive the same, not voltage this time, but the same charge. And one way to visualize that is to trace what the electrons will be doing in the circuit. So let's take a look at the electrons and see how they're going to behave in the circuit. If this is a positive terminal of a voltage source and this is the negative terminal, any electrons in the wire will be repelled from the negative terminal and attracted to the positive. So if electrons are going to be attracted to the positive terminal, we're going to find that this side over here is going to be mostly positive because electrons will be drawn away from this plate over here. Electrons, E minuses, will be drawn towards the positive plate. Likewise, electrons will be pushed away from the negative terminal of the voltage source. So if the electrons get pushed away this way, that means that this plate over here is going to be mostly negatively charged. And because this plate is negatively charged, it's going to push electrons away in this wire, going to push electrons away this way. And so this plate over here will be now negatively charged. And because electrons leave this plate right here, that means this plate is going to be mostly positively charged. And when the dust settles, we're going to find that this battery is going to have a plus Q here. This is going to have a plus Q here. This is going to have a minus Q here. This is going to have a plus Q here. This is going to have a minus Q here. And this will also have a minus Q over on that terminal as well. So all of the magnitudes of charges on each capacitor as they all balance will be exactly the same. So in series, each capacitor will receive the same charge. Let's look at the equation for equivalent capacitance in series. So this equation will look like this. 1 over C equivalent is going to equal the sum of all 1 over C's, or 1 over C1 plus 1 over C2 plus ... And as we discussed, this is the same pattern that we saw for the equation for the equivalent resistance in parallel. So once again, that flip-flopping of the pattern between capacitors and resistors in series and parallel. And we're going to find that adding a capacitor in series, just like it did in parallel for resistors, adding a capacitor in series will decrease the overall capacitance of a circuit. And we're going to see a pattern for that coming up as well. So as we said, adding a capacitor in series will decrease the overall capacitance of a circuit. What I'd like to do is provide an explanation for why that happens. So let's envision that we have a capacitor circuit like this, where we've got our EMF here, we've got a capacitor here, and a capacitor here, and a capacitor here. So 3 capacitors in series. What we've done by adding capacitors in series is we've provided extra distance. So if we call this distance D1, and this distance D2, and this distance D3, we're adding extra distance between the capacitor plates by adding them in series. But the area of the capacitors has essentially stayed the same. So if you look back at the equation for equivalent if we look at the equation for capacitance of a parallel plate capacitor, capacitance is equal to kappa, the dielectric constant, times epsilon naught, the permittivity of free space, times the, let's see if I'm good, times the area over the distance, right? Now, if this area is staying constant, and this distance, as you can see, is increasing because we're adding more space between the plates, an increasing distance in the denominator will cause this capacitance to reduce. So this is a conceptual way to think about why it is that the capacitance of a series configuration of capacitors will reduce as you add more capacitors in series. All right, I hope that was helpful on a conceptual level. Let's look at an example quantitatively. So here you can see we have 2 capacitors in series. We got the same 12-volt battery, and now we have a 2 microfarad and a 4 microfarad capacitor in series with one another. And we're going to see a very similar pattern here. We want to find the total capacitance, total charge, total energy, and then we're going to look at an individual capacitor, the 2 microfarad capacitor, charge, and energy. So let's start out with the total capacitance of the entire circuit, part A. We're going to say 1 over equivalent capacitance is equal to 1 over 2 microfarads plus 1 over 4 microfarads. Now, these numbers were chosen very nicely, such that they have a nice common denominator of 4. So 1/2 is 2/4 plus 1/4 is 3/4. So this is 3/4, or rather 3/4 microfarads. Or 1 over, I should say. 1 over microfarads. So 3/4, 1 over microfarads. And if we want to find the equivalent capacitance, we have to flip, like we said before, take the reciprocal of both sides here, and we get the equivalent capacitance is equal to the reciprocal of 3/4, which is 4/3, or 1.333 microfarads for the equivalent capacitance. All right, so we got part A down. Let's now find the total charge stored on this capacitor circuit. So in part B, we say Q total is equal to C total times V total. And the total capacitance we said before was 1.333 microfarads times the total voltage of 12 volts. So we have 4/3 times 12 is going to give us 16 microcoulombs of total charge. All right, so that takes care of part B for us. And let's look now at part C. So the total potential energy stored in this capacitor circuit is going to be 1/2 C total V total squared. So 1/2, the C total we said was 4/3 microfarads times the voltage we said was 12 volts squared. And if we take 1/2 of 4/3, we get 4/6 or 2/3 times 12 squared. And if we do that computation, we're going to get 96.0 microjoules of potential energy stored in the circuit. All right, so the next question was to ask for the charge on the 2 microfarad capacitor. All right, let's take a look. So that equation is going to be, we're going to call this Q2. Or rather, I'm going to call this Q1 just to be consistent with our notation from the previous problem. So let's label these capacitors. We'll call this capacitor here C1, and we'll call this capacitor here C2. So with that notation, we're going to call this the charge on the first capacitor, which is going to be the capacitance of the first capacitor times the voltage of the first capacitor. Now, we run into a bit of a challenge here in finding this charge because we don't know what this voltage is. So initially, we're a little bit perplexed. We're like, we don't know what that voltage is. We do know the capacitance, but how can we find the charge? That's where going back to this rule that we established right here can be so helpful to us. In series, each capacitor receives the same charge. So whatever charge we had in part B of this problem, that total charge, that will be the same charge on every single capacitor. So that 16 microcoulombs of charge, that will be our charge. That is the answer. Q1 is going to be equal to Q2, is going to be equal to Q total, is going to be equal to 16 microcoulombs of charge. So that was actually easier than expected. We have exactly the right amount of charge because every capacitor is going to have the same amount of charge, which is the total charge stored in the circuit. All right. So with that in mind, we can now, in part E, we can find the potential energy stored in the first capacitor, and that potential energy is going to be equal to 1/2 C1 V1 squared. Now, we don't have the voltage, like we said earlier, right? So V1, if we take this equation here, we can solve for the voltage, and we're going to get Q1 over C1. And so that charge Q1 was 16 microcoulombs, and we divide that by the capacitor of the first capacitor, which was, I believe, 2 microfarads. Notice that the micros do cancel. So 16 divided by 2 provides us with 8 volts. Is it plausible that in this first capacitor we would drop 8 volts of potential? Certainly it is, because we had 12 volts to begin with. So it's very plausible that we would drop 8 volts in this first capacitor. And based on Kirchhoff's loop rule, if we drop 8 volts in the first capacitor, then we must drop 4 volts in the next capacitor. So that's very convenient as well. So we have found the voltage V1 to be 8 volts. So now we're going to say the potential energy is 1/2. C1 is the 2 microfarads times 8 volts squared The 1/2 and the 2 will cancel. 8 squared is 64. So we're going to have 64 microjoules of energy. So is it plausible that this capacitor would store 64 microjoules of energy? If we go back to the total energy stored, yes, it is plausible. We're going to find that if our total energy was 96 microjoules, it is plausible that that capacitor would have stored a fraction of the total, or 64 microjoules. And that concludes these basic concepts of capacitor circuits with both parallel and series capacitors. In our next video, we're going to take a look at RC circuits. All right, thanks for watching.